Technological University in Singapore. Professor Chandra is also director of the Satellite Research Center at Nanyang Technological University, which has extensive experience in small satellite development over the past 2 decades. So Amal today will share with us some of the work that's been going on at NTU and some experience and lessons learned on their various smallsat projects. Okay, so Amal, whenever you're ready.
Thanks, Lauren. Special thanks to Professor Yip for inviting me to give this talk. It's my privilege to give you an update about the various missions at the Satellite Research Center at Nanyang Technological University. I've collaborated quite extensively with National Central University, and we hope to continue this collaboration and do a lot of exciting science together. So my name is Amal Chandran. At NTU, I'm an assistant professor at the Electrical Engineering Department. My background is in mechanical and aerospace engineering, so it's a slightly different department. I'm pretty much the only guy doing space science and a little bit, mechanical engineering focused work. But the Satellite Center sits under the Electrical Engineering Department, and it's very interdisciplinary, and we get a lot of students from other schools as well. So I'd like to talk to you a little bit about, how we conduct our student programs and how we try to attract both undergraduate and graduate students and keep a supply chain of students that we use for various engineering work at the center. I also teach an engineering curriculum focused on spacecraft design. That's been a challenge because I'm pretty much the only faculty that has a space engineering background. So I teach a couple of preliminary spacecraft design classes, and I always try to tie it in with the missions that we are working on. So to give a brief history of the Satellite Center, the center was established in the latter half of the last decade. And the primary objective was to build Singapore's first satellite, the XSat. And that satellite was built and launched in 2011. It is still working. It's an imaging satellite. It's at an orbit of about 780 kilometers. It was launched by the Indian Space Research Organization's PSLV rocket. It was a dedicated launch, and the satellite's still functioning, by which it's not imaging anymore, but it's still operational. We have contacts, but we are going to be decommissioning that satellite this year. It's been 10 long years, and I think it's way past its design life. So we're very happy with that. Then what happened? So it was a 100-kilogram satellite also, about 1 meter cube, 100 kilogram, at the higher end of a microsatellite, almost a small satellite. Then what happened was Singapore has this very intense interest to commercialize everything that we can. So the entire team that worked on this satellite got spun off into ST, Singapore Technologies Satellite Systems, ST-SATSys. And ST-SATSys is a joint venture between the Nanyang Technological University, the Defense Science Organization, and ST. And they've continued to build small satellite platforms and imaging satellites. The center, however, was left with a serious dearth of manpower and corporate knowledge that went with the creation of this entity. So we focused on training students, and from a 100-kilogram satellite, the second satellite we built was a 1U nanosatellite. So, but this was almost entirely built with students. So that's the second one that you see in this chart. I hope you can see my cursor. So this is the second satellite that we built. And then we built a 3U with an expanded telescope to improve the focal length and get higher resolution imagery. That one only worked about a couple of weeks. There was an SCU event, and the satellite went dead after that. There was a solar storm, and many satellites, unfortunately, died at that time, and ours was one of it. The next two satellites were a 6U satellite, and then we did a radio occultation payload on a 130-kilogram satellite, which we actually was the mission managers, but the spacecraft itself was built in Korea, the platform, but we were the mission managers, and we continue to operate that satellite as well. After that, we had a couple of small 2Us and 1.5U that we built. These 3 satellites we built in collaboration with QTech. We had some pulse plasma thrusters, and our idea was to see if we could use pulse plasma thrusters for attitude correction. And we flew a chip-scale atomic clock on this 2U to space qualify the micro-semi chip-scale atomic clock, and then look at it over multiple ground stations to see ionospheric scintillation due to signal passing through different regions of the ionosphere, and you would have plasma in one region versus not in another, and you would see from the scintillation you would see you could get the ion content. Currently, we are building 4 satellites. We have 2 27U spacecraft. So 27U is at the higher end of CubeSats. These are 30 by 30 by 30 centimeter cubes. And we have 2 3U satellites, similar to IdeaSat that we are building right now. So as you can see, there's a number of spacecraft that we have built and are currently building. And in this talk, I will talk about the Arcade spacecraft, the 27U, that we expect to launch in June of 2022. That's the tentative launch date that we've been given. And we have a flight readiness review that is scheduled for December of 2021. And I'll also talk about the twins, Scoob-1 and Scoob-2, or as we like to call it, Scooby and Scooby-Doo, which are also scheduled for launch along with the Arcade spacecraft in June of 22. So the satellite center, it's a fully functional center within the university. It's very interdisciplinary. We have faculty from electrical engineering, computer science, mechanical engineering, various faculty that are involved in different aspects or research interest areas. So these also cover material science, thermal management of satellites, RF communication systems, etc. Not very much in the payload space as yet, and we are hoping to change that in the future. Having built all these micro and nano satellites, one good thing about the facility is that we have facilities for the entire life cycle of the satellite. So except for a shaker, for vibration testing, which we go outside of the university, we have everything else to design, build it, and test the spacecraft. So we usually contract with ST, Singapore Technologies, for the vibration testing, but everything else we do in-house. We also have ground systems where we have 2 UHF antennas, and then we have a 6-meter dish with S and X band downlink and S band uplink. So we can cover downlink in UHF, S band, and X band, and uplink in UHF and UHF, VHF, and S band. Okay, and I would like to also say that the team comprises of full-time engineers. So we have a team of currently about 8 engineers that work on many subsystems, and then we have a number of student interns, and finally a project students, as well as graduate student interns that come in and work at the center. So the first spacecraft that I will talk to you about is the 27U spacecraft that we call Arcade, or the Atmospheric Coupling and Dynamics Explorer. It is also the 4th satellite in the INSPIRE series of missions. And right now, and the main partner, is Singapore, which is building it. Germany and Taiwan are significant partners providing hardware to the mission as well. So the science of motivation for the Arcade mission is to study the variability in the equatorial ionosphere and characterize lower and upper atmosphere coupling. So I think you might have heard a few talks on aeronomy and the upper atmosphere and how small satellites can help in characterizing the ionosphere and looking at the wave dynamics and coupling. So Singapore, being equatorial, likes to launch its satellites onto an equatorial orbit. So the good thing about that is that unlike polar orbits, we see the satellite every 90 minutes. So as the satellite goes around every 90 minutes, every orbit we have a pass. So Singapore is what, 1.8 to 1.9 degrees north of the equator. So we see it all the time. Commissioning is a pain because you recover from it over one pass and it's already time for the next. But the equatorial ionosphere is also very exciting because that is where you would be passing through the four-peak structure in the magnetic equator. So this is right where a lot of traveling ionospheric disturbances and plasma enhancements are seen in TEC. So this is an exciting region to be sampling in situ. So we are carrying the compact ionosphere probe that flew on IdeaSat, and there's a miniature version of AIP on Formososat. So we hope to be able to look at the equatorial ionosphere with the CIP, and very excited about getting plasma information at a lower altitude. And I'll talk about that aspect of the mission very soon. The other part of all of this is that the ionospheric plasma is, of course, being driven predominantly by changes in solar effects, but lower atmosphere forcing also plays an important part. During quiet solar times, when there is no major solar storm, it has been estimated that up to 30% of the ionospheric variability can be driven by forcing from below. So again, we want to look at neutral dynamics. So the wave coupling between the lower and upper atmospheres has a large role in what we see in the F region. So we want to look at these non-migrating tides or gravity waves from the lower atmosphere, and hence we have a infrared imager that we look at atomic oxygen emissions to characterize gravity waves in this region. Yeah. This is the satellite configuration. As I mentioned, it is a 27U. This is the CAT model of how it looks like, and here you can see CIP on it on here. So this is the RAM phase of the spacecraft. I actually believe this has changed a bit from this configuration, but this large-looking telescope you see, this is the infrared imager that we use for the for looking at waves in infrared emission from atomic oxygen. Here these are battery packs inside. This is a thruster, and I'll talk about the thruster. This is the S-band patch antenna. Actually, that has been changed. So this is a slightly older version. We have changed from S-band to X-band on this mission. And this is the avionics stack. So as you can see, we have two power boards here, and I'll talk about why we need that. And we have an X-band transmitter on top of that. Yeah. So that's what the spacecraft looks like. And this is various stages of where we are right now. So the top left picture is the flat sat, and you can see where the avionics stack, it's not the completely assembled stack, which you see here, where we have the X-band now on top of it. This is the engineering model of an Earth imaging camera that we have. This is the infrared imager. CIP simulator is in here somewhere. We have the UHF, SpaceQuest UHF that Lauren's been talking about, that they flew on IdeaSat as well. So there's quite a number of components that are common, and we have the flat sat all laid out. One interesting thing to see, what you see here is our, this is our passive radiator. So the infrared detector needs to be kept at about -4 degrees Celsius. So we have a rather large radiator that we use to radiate energy to cold space to make sure that it is well within that thermal range. And this is the integrated avionics stack with all the boards in there. This is the engineering model of the structure coming together. And here what we have is a spacecraft and antenna in an anechoic chamber where we are looking at the antenna pattern. So one of the lessons learned from previous missions has been to integrate fast and test as early as possible. And here what you see was our first TVAC test that we did about 10 days ago. So we integrated the Atmolite imager, the avionics stack. This is where CIP will go through. Once we have CIP, that's the, so this is the engineering model of the structure. We put one of the solar panels on. We didn't put the other ones. We have 3 deployable panels and 1 body mount panel. We get about 84 watts of power from these. Each panel has 21 cells. So we have 84 cells, and we get roughly 100 watts of average power on this. So it generates quite a bit of power as well, the spacecraft. And you can see how big the spacecraft is. And this is where the electric propulsion thruster goes on the ring face. The mounting ring that connects the spacecraft to the launch vehicle is over here, which is essentially this one. and in the middle of that ring is where the thruster goes. And these small slots that you see are for the fine sun sensors that go on board. Okay. The mission profile is quite interesting. We have roughly a 2-month period, 2-year period rather, for the science operations. We get launched and put into an elliptical orbit, which is 535 by 450 kilometers in an equatorial orbit. And that's our nominal science orbit, where we will operate for 6 months, collect science data, and do checkout of all the subsystems. The second phase is an orbit reduction phase, where we reduce our orbit to 350 kilometers. And this phase is expected to take about 3 months. With an electric propulsion thruster, you have very high specific impulse. So your total thrust per kilogram of the fuel is very high, but your thrust is very low. So you need to lower your orbit over quite a long period to be able to come down to 350 kilometers. And the thruster is a high power system. It takes a lot of power. So we don't operate the instruments during this phase. Our third phase, once we are in our desired what we call VLEO, or very low Earth orbit, we go into a nominal science phase again for 2 months. During this phase, aerodynamic drag will cause the spacecraft to deorbit to about 325 kilometers. And then we start the firing again to increase our orbit altitude for about 3 months. And then we will be doing nominal science and imaging till end of mission. And we expect it to be about 3 months. So this is what the orbit simulations look like. Initially, we get deployed in our elliptical 530 by 435 kilometer orbit. And then we have an orbit reduction phase, where we fire the thruster to come down. We have 2 months of VLEO phase, 3 months of orbit boost after that. And then this is our second VLEO phase and end of mission as we come down. And we have modeled this using NRL MSIS drag model and F10 at 150 high solar activity. So another factor that we have to consider is the enhanced aerodynamic drag at lower altitudes, and whether our attitude control system can account for the high aerodynamic torque. To correct for the aerodynamic torque, you need you need to generate counter torque using your reaction wheels, which means you need larger reaction wheels. And then to despin or desaturate your reaction wheels as they get saturated, you need larger torque rods. So we've been working with Blue Canyon for their exact attitude control system, and we have gone with larger wheels and torque rods than what we have flown on InspireSat 2 and InspireSat 1, rather IDSat and InspireSat 1. And this is what the disturbance environment looks like. And what is interesting, if you look at the magnitude of the drag, the disturbance torques, you'll see that aerodynamic torque at, so this is on the left, what you see is at 350, and what you see on the right is at, this is at 450 and this is at 350. And you can see that the aerodynamic torque actually increases by 2 orders of magnitude as you come down in altitude. And if you look at these numbers, 10 to the minus 7, 10 to the minus 9, 10 to the minus 8, you'll see that aerodynamic torque is the predominant factor here compared to everything else, which is solar radiation pressure, magnetic torque, and gravity gradient. So if you take all of the disturbance torque, you're easily being dominated by the aerodynamic torque. And that's the one that you have to compensate for. Another factor that you will see is that the neutral density changes quite a bit. So the aerodynamic torque depends, of course, on the neutral density of the atmosphere at that altitude. So if your density is high, you will have more aerodynamic drag. So we've looked at that. We've looked at MSIS, using MSIS, which is the one that we have used in our orbit propagator models. And we've also looked at the whole atmosphere model from NOAA. And we've looked at how the aerodynamic drag force or the neutral density varies at 350 kilometers in an equatorial orbit during storm days and non-storm days. So for example, if you have a solar event, your satellite may not be where you expect it to be because your neutral density is going to increase. So here what you see is density with longitude. So this is, say, nighttime versus daytime. And you can see that WAM and MSIS have a fairly good correlation, which is pretty nice. And this is with latitude. And we are operating somewhere in the in the equatorial region, where thankfully it's less. Of course, this also changes with local time, right? So this is at one local time. Now, compared to a storm day, so this is an example of March 17, 2015, where you had a solar storm, you can have 2 to 2.5 orders of magnitude difference in your atmospheric density just from MSIS and what you see from WAM. So WAM is more physically more realistic because you have essentially a higher, all the physics where the lower atmosphere forcing, for example, is captured, whereas in MSIS it is not. So you can see a clear difference in density. And these are the kind of things that we are actually preparing for and trying to compensate for on orbit. So thruster specifications, we have an iodine propellant thruster. So we went with a French company called Trust Me, and when we went with them, initially they had a xenon thruster. They have since then flown the iodine system, so give us a lot more confidence on the iodine propulsion system. And the thrust actually is variable from 0.4 to 1.1 millinewton. We are working at about 0.8 millinewtons and provides up to 5,500 Newton seconds, and it operates at between 30 to 65 watts. So the higher the power, the larger the thrust you get. And I believe we supply it at 12 volt in this. So this is the performance curve, and here what you can see is, as for the different power levels, what the output thrust is. We are operating at about 0.8 millinewtons. So and our power level is about 55 to 60 watts. And here you see the startup power and then what it is during during its operational phase. And you can see the thrust fuel budget here as well, about how much propellant we expect to use for different phases of the mission. So the on-orbit performance, as I mentioned, they have actually flown the thruster, and you can see that they've achieved about 0.8 millinewtons of thrust during their firing phase. So this is measured on orbit and gave us a lot of confidence just before the flight delivery. And this is from GPS, how the altitude has been changed by 200 meters during this firing phase. So they've fired for about a couple of hours, and the altitude increased by about couple of hundred, about 400-500 meters here. So it's been shown to work, which is great news. I'll talk a little bit about the instruments on board. We have an instrument called Atmolite, which is a spatial heterodyne interferometer. Basically, what that means is that it takes the light. It has a beam splitter, and it has an interferometer that focuses the light back and produces interference patterns. And these interference patterns depends on the grating and how they are aligned with respect to the beam splitter. You get the brightest band, the central at the literal wavelength, and you can measure 0.1 nanometer in wavelength from the literal band. The brightness of these interference pattern depends on the intensity of the emission. The intensity of the emission, in turn, depends on your background temperature. And the atomic oxygen is in equilibrium with the background temperature. So from the intensity of the emission, you can directly derive the background temperature. So we get altitude profiles from this. And based on the temperature of the altitude profiles, you can find the wiggles and do a Fourier transform on these profiles and temperature perturbation to get wave structures from the upper atmosphere. So that's what we are looking at, and we'll be looking at gravity waves between gravity waves and tides. As if we get a long enough measurement record, we'll be looking at gravity waves and tides between 80 to 140 kilometers in the mesosphere and upper thermosphere. To do that, what we do is we look at the limb of the atmosphere. So if the spacecraft is flying in this direction, we will be tilting the spacecraft to look at the Earth's limb. And this is the, and we'll get we have a 60 by 60 field of view, and we will be they are getting waves in that field of view. And as I said, we are looking at the atomic oxygen emission at about 765 nanometers, and again, the atomic oxygen is in equilibrium with the background temperature, and the emission strength depends on the temperature of the atomic oxygen. And at daytime we get 80 to 140, and at nighttime we get 85 to 100 kilometers where you see atomic oxygen. Right. We have CIP as well, and I think you know about CIP. I don't need to talk too much about it. We'll be running it possibly at 1 and 8 hertz because we want to look at the fine ionospheric structure in the equatorial ionosphere. We hope to be running it in all 4 modes. And the main questions that we want to ask are, what are the occurrence rates and characteristics of plasma irregularities at low latitudes? We'll be seeing the region between plus or minus 10 degrees of the equator. What are the spatial and temperature variations of the thermospheric midnight temperature maximum, and the morphology of ion density and electric field in the equatorial nighttime ionosphere? Midnight temperature maximum, something we wanted to really address with InspireSat-1, but we could not, because now the launch, as I hear, it's a ride share, of course, and we are possibly going to be on a sun synchronous orbit, so we might not be able to see many local times, which is what we want to look at to see the midnight temperature maximum. So if you look at the plasma temperature, it follows this curve, but very often in observations we see a bump just after local midnight, and we want to explore what causes this spike in temperature that is very localized at local midnight in low latitudes especially. So I'd like to use the rest of the time to talk about 2 fun missions that we are doing, the Scooby and Scooby-Doo missions. These are 3U satellites entirely designed and built by a team of students at NTU. So when I came to NTU, one of my primary focus was to develop an engineering curriculum. I like to teach hands-on engineering, so I like to take in a team of students and have them work on stuff rather than have them sit in classrooms and have boring lecture after lecture. So the first satellite was entirely because we have this PSLV rocket that Singapore government has bought, and there are opportunities to put multiple CubeSats on it. We said, okay, we are going to build a 3U internally funded by the center with help from the electrical engineering department, and use it for student training and get it to space. So it's near equatorial again, 500-kilometer altitude, and a 3U, classic 3U size. Actually, this is not right for this one. We descoped this and we just have a passive magnet. So you have a passive magnet that will produce a torque with relation to the Earth's magnetic field and will align the spacecraft, and it will spin on the 3rd axis. So it's a passive magnet additive control system, $10 ADCS. And the payload that we have is a spectrometer that we have built in-house. So we have taken CORDS IR visible UV spectrometers and built a what we call a CORDS solar irradiance monitor. And then we've also built an RDUCam visible camera that we hope to get about 30-meter resolution from on orbit. Okay. Again, measure the mission objectives, measure solar irradiation using CORDS multispectral sensors in visible, near IR, and UV. Build a visible camera to image the Earth. Test our ADCS. Actually, that's in Scooby 2, not this one. Hands-on education. So this is the main objective, and what you see here are students working on stuff during their final year projects. So the educational system here, undergraduate students in the final year have to do a 1-year final year project that they can sign up with professors who give the project descriptions, and we can select students. 3rd year, there is a design and innovation project where students work on teams of 10. And then I also hire undergraduate students and student interns. So our project management and systems engineering are done by PhD students, and then we have FYP and a mix of PhD, DIP, and volunteers. These are SETS volunteers, Students for Education and Development of Space. I get a lot of requests from students wanting to do something with space. So I say, okay, come in and talk to these students who are working on the satellite. And if you are interested, come and help out with this mission. So it gives them a chance to really understand if they want to do space engineering. So interest in space is very different from actually doing the work. So I found that a lot of students are interested in space, but when it comes to the mundane engineering tasks that need to be done, their interest can disappear very quickly. So this also gives me an opportunity to select the students who are genuinely interested versus people who have a passing interest in space but don't want to, kind of do the hard work. So we've had quite a number of student participation, and we roughly have had about 53 students work on Scoop 1 so far. With the mission started in about August 2018. Right now we are at the engineering model phase. We are doing environmental testing for the engineering model right now. In fact, I was telling Professor Lauren that we had an incident where we had a small accident and a couple of students cut their fingers, not too badly, but yeah, so it's been exciting. We're doing some environmental testing, hoping to complete it in a couple of weeks and have the flight model integrated and tested over the summer. That's what the spacecraft looks like, Scooby or Scoop 1. And Scoop 1 is S-Cube, Student Satellite Series, so S-Cube 1 became Scooby. But this is what it looks like. We have body-mounted solar panels, quad-pole UHF antenna, and then we have the multispectral sensor on 4 sides. So this is the long axis is the one that aligns itself with the Earth's magnetic field. So as you go along an equatorial orbit, you're going like this. So your monopole antenna is actually, it's not a quadrupole. It's a monopole antenna pointing along the long axis. So we should be having good contact. And then as it goes around, you have and it's spinning around this long axis as well. And you have multispectral sensors that will be able to get look at the solar irradiance as we do it. So it's a very simple satellite, but it's great for students to understand the engineering that goes into building a satellite. We have not spent a lot of time developing hardware. We have actually taken an Endurosat OBC, EPS, and UHF for Scoop 1. And you'll see that things are quite different in Scoop 2. And we've built our Scoop 1 payloads. We've taken the UV sensors from basically SparkFun. So it's the SparkFun Triad sensor. So we scoped out these same sensors. We tested out it with this board. Then we bought these individual sensor components and assembled it in our own multispectral payload board. And that's what the payload looks like. And on this we have UV, nanometer, and visible, as I said. So we have about 18 channels that we can measure from 410 to 940 nanometers. So another thing that we have done is solar panel development. The students have really gotten good at assembling solar panels. So we've done we can see 1U panels that we built initially. And then the students have started building 3U panels, and it's gotten really good. This is the engineering model. So this is the engineering model in our test chamber. And as I mentioned, it's not a quadrupole antenna, it's the monopole antenna, very similar to the IdeaSat antenna with heritage from LASP, same thing that we've used. And this is the avionics stack all integrated. And I think this is a video.
Please wait for 10 seconds and we'll stop. 10 seconds.
So what we are doing here, this is our TVAC chamber, and we are deploying the antenna inside the TVAC chamber. Sure. I can see the deployment. So yeah, so it's been through cycle already, and things are looking good. It's a great mission to train students. So we talked to our funding agencies about the Scoop 1 mission, which started in 2018. Then our funding agency came back to us and asked, can you build a 3U for flying one of our payloads? So our main funding agency is the Defense Science Organization. It's supposed to be a private entity and civilian, not a military facility, but they do a lot of classified research. So we didn't get to ask too many questions about the payload, but I said, why not? It'll give the students a good experience of working with an actual customer. And I, of course, said, we can't give you too many documentation like we would do with a fully funded mission, because this is being done by students. So documentation will be in the presence of, it will be in the form of slides and presentations, and the funding agency was okay with that. So we have a 3U satellite, but it has deployable solar panels. And now, because we have deployable solar panels, we need to point to the sun. So our pointing determination accuracy has to be less than 5 degrees. So here we have fine and coarse sun sensors, magnetometers, reaction wheels, and everything that we need here. Okay, and that's what the satellite looks like. Provide a spacecraft for accommodating customer payload, operate payload for 10 minutes per orbit, store and downlink payload telemetry, and train students. So that's the objective. Again, I'm the PI on this mission. Project management, systems engineering are done by students, but we actually have put our full-time engineers in key positions so that they can provide the overview of the mission, and then most of the work is again done by graduate students. And mission timeline, we have to have a December flight delivery for this year. Right now we've passed PDR in December of last year, December 2020, and we are in the EM assembly phase. And this is what the spacecraft looks like in the deployed and stored configuration. The major change is an ADCS system that we are putting in. So this is one of the major developments that we are doing. The CNDH and EPS are heritage systems from InspireSat-1. So we have used the InspireSat-1 CDH, InspireSat-1 EPS. We've miniaturized those into 10 by 10 boards using the Space Quest radio. We're using the same InspireSat-1 battery pack. So almost all of the avionics is the same. We've taken the CIP interface and put the payload in there. And then we've used the ADCS interface. We're redesigning this ADCS, which flew on Velox 2, to now fit in with the exact interfaces that we use for IS-1. So what the architecture philosophy we've used is to reproduce as much of Inspire-1 as possible to save on the engineering time and effort. So this is the ADCS that we are developing, and I'm keen to make this available for the Inspire consortium, because this will give us a rudimentary ADCS that does not have a star tracker, but for anything that is less than, say, 5 degrees of pointing precision, we can use it for active pointing. And it's, of course, an order of magnitude less costly than the exact. So this is the attitude determination board that we are building, where we have all the core sun sensors, fine sun sensors, magnetometer, gyroscopes, implements the Quest algorithm, implements ACS algorithm as well. You can see the Arduino M0 processor board that we use. This was the preliminary version, but now we have incorporated this into our board as well. It looks a lot better. We have actually an ARM Cortex M4 microcontroller at the core of the system that does this. And this is sensor testing, where we are calibrating the sun sensors. So basically, you put the sun sensors and you look at the RMS error along the field of line in 2 axes, and you have to calibrate it for each sensor so that you know what the RMS error is, and then that translates into the attitude determination that you do. So I have a lot of students doing this work on a turntable. So we have a sun simulator here, and then we have a 2-axis table, and then we use that to calibrate the sensors. So this is the risk metric that we show the funding agencies, that of course one of the deployables may fail, which is when you have deployables, that is a major risk. Delay in ADCS development, because most of the ADCS development is being done by students. That is something that we are keeping track of. Payload heat management. The customer payload is a high power 30-watt payload. So we only operated for 10 minutes, but the heat management is one of the main challenges here. And then appropriate and timely student recruitment. This is very, very difficult to get students in. Make sure that they stay in throughout the program. That is a major concern for us. And you'll see that is the one that I have rated the highest. How do we keep their interest? There are 2 courses that I teach for spacecraft design. One is an undergraduate and one is a graduate course. And mostly the students get to work with hardware. So some students really love it. Some students think they like it, but ends up they don't. And then, we get PhDs, postgraduate students, final year thesis students, design students from 3rd year, and interns and volunteers. So we don't say no to everybody, but there's some filtering that happens automatically. To recruit students, we make flyers for each of these departments. So this is for the arts and design school. This is for the mechanical engineering. This is for I think this is for electrical engineering, and this is for computer science. So we put it in different departments and try and attract students to come in and talk to us and see how we can and see how they can help with the program. So in summary, I just wanted to share some thoughts about building satellites within a university. One of the things that has come out from building all of these satellites with students is better mentorship. PIs are always busy with multiple projects. So I'm PI on these 3 missions here, plus the InspireSat-1. So I have 4 missions going on, plus my own research, my teaching. And if students don't come to me, I assume everything is fine, which is never the case, right? So getting right mentorship to students, making sure that these are delegated with full-time engineering support is, I feel, very, very important. And I have some comments and reviews on the next slide that I'll share, that I'll talk about. Better documentation. Templates are not always present. So we have had continuity problems in these programs. And the documentation is never at the stage where, sometimes we have a lot of documents, but they are not filled in properly. So the right information may not be captured. Another lesson we learned was start integration early. So a subsystem may be done, but unless it works together with everything else in an integrated setup, it's not really done. It has to be confirmed to work in an integrated setup. So test systems early, make system level tests early. So these are lessons that we've learned. Freeze hardware changes. Don't get into a flight build as early as you can. Don't keep making hardware changes. Reviews, definitely we need to do better on those. Instead of one day end of summer or end of semester review, we are making those a pre-review presentation. The next 4 weeks, the students use to generate detailed documentation to send to the review board by end of August. And then the review board sends comments over the next month or so. And then we have a follow-up video conference. So this, I think, captures the comments and the action items a lot better than the one-day reviews that we currently have. And these are some of this is, I think, the DIP students that worked with me last year. And that's all I have. I'll be happy to take any questions.
Thank you very much, Amal, for a very detailed presentation of all the work that goes into running a university small satellite program. Does anyone have any questions for Amal? If you have a question, please feel free to raise your hand using the button below your screen. If not, I have a quick question for Amal. So you mentioned that reviews are, again, quite important. Just out of curiosity, what sort of review panel members do you typically invite?
So it depends on the mission profile, right? So in our mission, we invite members from the technical board of DSO, which funds our missions. They have to be on the review panel. And then we also invite, for Arcade, we have invited people from Germany, people such as yourself, LASP, and IAST to join in on these reviews. So again, it's been, so far all the reviews we have done have been one-day reviews. except for with DSO, the last time that we did a review, we actually did it over a period of time. So we had the one-day review, which was what we called a pre-review. And then the next couple of months were spent actually on the documentation to capture everything and address all the concerns that they had.
Okay. As I think you're aware with IdeaSat, one of the issues that we've been facing is the appearance of an anomaly that apparently did not come up during ground testing.
Yeah.
Do you do any type of longer duration burn-in testing or operational testing on the ground, something longer than your typical TVAC?
Well, we have run the spacecraft for 2 weeks. So 2 weeks with the solar array simulator on a mission configuration. So what that helps us to do is that, as you know, we have different modes of operation that depends on the battery state of charge. So we changed the orbit insolation and the eclipse times on the solar array simulator and let the spacecraft run. So we can see, how the battery charges, for example, and whether the mode switching is happening. The longest we have run it is for 2 weeks. We are also worried about loss of power in the lab that might happen, in which case we have about three hours before the battery completely discharges, right? So that is a concern. And I'll say the most we've done is about 2 weeks. We have not run it longer than that. After IdeaSat, I'm tending towards making at least a month run, which would be nice.
Yeah, likewise for us. Also, when you guys run into an anomaly with an operational spacecraft on orbit, do you guys have a typical procedure that you guys go through?
Yeah, we try to reproduce the anomaly on the flat-sat or the engineering model on the ground. So this involves, before we check out the spacecraft for after our flight readiness review, we also do a checkout to make sure that the same version of the code is running on the flat-sat. And we have as much components integrated as possible. So as you know, the exact is very expensive, and we may only have one unit of the exact. So we may not have another exact with us on the ground, right? But and when we have an anomaly, we try and reproduce what we have seen on the flat-sat if we can. So that is one method of anomaly resolution. And I speak from experience when Mings 2 had the anomaly. They were able to reproduce the constant initialization loop that the spacecraft probably ended up in by sending the spacecraft reset command in sunlight, which was sent in on the flat-sat when it was connected to the solar array simulator. So in sometimes it really helps, but there is no way of confirming that could have happened, right? That's exactly what happened, but it gives you a high probability that you can find something that probably did happen.
Absolutely. What we're trying to do right now is basically trying to reconstruct at the very least what is likely to have happened based on a review of the flight data, and then essentially constructing a flat-sat after the fact.
Yeah, and as I understand it, you only had one UHF radio as well. So you don't have a UHF radio on the flat-sat.
Yeah, that is one constraint. Also, import of RF components into Taiwan is also heavily restricted. Yeah. Does anyone have any additional questions for Amal? Okay. It looks like everything was very clear. So thank you very much for phoning in, and we appreciate your devoting an hour of your time and during this busy time. I hope everyone's fingers are okay. Egos.
Yeah. Lessons learned, right? Use the clamp.
Yep. Okay. As long as no one died or was severely maimed, then it's good.
It'll work well.
Okay.
Bye.
Thank you very much, Amal.